You ever stop to think about how much time even like the fastest computer programs spend just,
Yeah.
well, waiting?
Yeah, it's kind of surprising, isn't it?
It's kind of wild when you think about it. Even super efficient code just sitting there idle.
Mm-hmm.
And that might resonate with you,
Yeah.
because you're here tuning in to gain knowledge quickly, efficiently,
Right.
just like a program should ideally get its tasks done without all that waiting around.
And what's really interesting here in Python, there's a pretty smart way to handle this waiting game, especially for programs doing a lot of I/O.
I/O, input output like network stuff.
Exactly. Fetching data online, talking to databases, that kind of thing. It's called asynchronous programming.
Okay.
And it's really a fundamental shift in how you approach certain kinds of programming problems.
Okay, yeah, let's maybe try and unpack that. Like, with an analogy, remember our restaurant of thread bots?
Oh yeah, the thread bots. Hey.
Right. But imagine instead of, lots of robots potentially bumping into each other, we have just one, a single super efficient loop bot.
Okay, a loop bot. I like it.
Now, when this loop bot has to wait for the kitchen, maybe an order's not ready, it doesn't just stand there.
It finds something else to do.
Precisely. It cleverly switches to another table, maybe one that's ready for the check or
Mm.
needs drinks refilled. No wasted time.
That's a great way to picture it. That's the core idea, really. Instead of blocking, just waiting,
Mm.
the program switches to other tasks that are ready.
And in Python, the tool for this is Asyncio.
That's the one, the Asyncio library.
Yeah.
And that's what this deep dive is all about, exploring Asyncio, the tools it offers for this non-waiting style of code,
Right.
and the actual problems it's really designed to solve. We're using Caleb Hatting's book, Using Asyncio in Python, as our guide here.
Now, I have heard, even from really experienced Python devs, that Asyncio can feel a bit intimidating.
Yeah, and it has that reputation sometimes.
It's complex to get started with, maybe a bit confusing.
It can seem that way. The syntax was a bit trickier in older Python versions, too.
So our mission today is to try and cut through some of that, focus on the key ideas, right? Why is Asyncio actually important? What's the benefit for certain tasks?
Exactly. We want to give you a really clear picture of what Asyncio is, why it's so good for those I/O-bound jobs, again, network stuff, databases,
Okay.
and how it stacks up against, the traditional way of doing things with threads. It's about how the program manages its time differently when it's waiting on external things.
All right, sounds good. Let's dive right in then. What's the fundamental problem Asyncio is actually trying to fix? Why do we need it?
So the number one thing, the crucial thing to get, is that Asyncio really, really shines with I/O-bound workloads.
I/O bound. Okay, keep saying that. It means lots of waiting.
Lots of waiting. Your program spends most of its time just waiting for something external to happen. Downloading a file, getting a database result.
Hmm.
The CPU isn't sweating. It's not crunching huge numbers. It's mostly just .idle, waiting for data.
Okay, that makes sense. So if the program's just waiting a lot, why not just use threads? We know threads, they handle doing multiple things. Why Asyncio?
Good question. There are two really big reasons. First, Asyncio is just a safer way to handle concurrency compared to threads.
Safer. How so?
Threads use what's called preemptive multitasking. The operating system can interrupt a thread basically anytime it wants and switch to another one.
Okay.
Remember our thread bots in the restaurant and Hatting's cutlery example?
Vaguely. Refresh my memory.
Okay, imagine multiple thread bots trying to update the same count of knives and forks.
Right. Shared cutlery pile.
Exactly. You've got a shared cutlery object, let's say, and several threads are doing something that looks simple, like self.knives plus 1, 1.
Yeah, just adding one. Seems straightforward.
But it's not. That pluses is actually like 3 steps internally. Read the current number, add 1 to it, write the new number back.
Ah, okay. Read, modify, write.
Yep. Now, because the OS can interrupt anywhere, imagine threadbot A reads the knife count, say 10 knives, then bam, OS interrupts it, puts it on hold.
Okay, threadbot A is Paul's mid-thought.
Right. Now threadbot B comes along. It also reads the knife count, which is still 10, right? Because A never finished writing.
So 10.
Threadbot B adds 1, gets 11, writes 11 back, finishes its job.
So the count is now 11 knives.
For a moment. Then threadbot A wakes up. It already read 10 way back when. It adds 1 to its number, gets 11, and writes 11 back.
Oh, so the update from threadbot B just got overwritten, wiped out.
Exactly. You just lost an update. That's a race condition. You end up with the wrong number of knives, inconsistent data, and it's super hard to figure out why. The core issue is those unexpected interruptions with shared data.
Yikes. That sounds like a nightmare to debug.
Yeah.
How do threads normally deal with this cutlery chaos?
The standard fix is using locks, like putting a do not disturb sign on the cutlery. You put a lock around the code that modifies the counts. Only one thread can grab the lock at a time, so only one thread can change the numbers, ensuring it finishes the read, modify, write sequence without interruption from another thread trying to do the same thing.
Right, that makes sense.
But it adds complexity, a lot of complexity. You have to identify everything that's shared, you have to make sure you acquire the lock, and crucially, release the lock correctly, even if errors happen.
And if you're using someone else's code, a library.
Exactly. It gets really tricky. You might not even know how they handle threads internally, or if you need to add your own locks. You could introduce a race condition without even realizing it, just by how you use a library.
Okay, that sounds like a good reason to be cautious. What was the second big reason to prefer Asyncio for these I/O things?
The second one is about efficiency, specifically with the CPU. Asyncio avoids the OS constantly switching between tasks on, say, multiple CPU cores when those tasks are mostly just waiting for I/O anyway.
Oh.
Think about it. If your program is just waiting for a web server to respond, the CPU isn't the bottleneck, right?
Right, it's the network or the server.
But with threads, the OS scheduler doesn't necessarily know a thread is just waiting idly. It'll still give it little slices of CPU time, switching away from other threads, switching back.
Even if the thread can't actually do anything yet?
Exactly. This constant switching, context switching, has overhead. It takes time and resources just to manage the switching itself.
So it's like paying a supervisor just to keep checking on workers who are waiting for parts to arrive. Not very efficient.
Perfect analogy.
Mm-hmm.
Asyncio, on the other hand, uses a cooperative model. Coroutines, the Asyncio equivalent of functions, explicitly say, okay, I'm waiting for this network thing now, I'll let you know when I'm done. They yield control back to the main manager, the event loop.
So they politely step aside.
Precisely. This means the event loop only runs tasks that are actually ready to make progress. It doesn't waste CPU time checking on tasks that are just waiting. So for I/O-bound stuff, it's often much more efficient with resources.
Okay, cooperative versus preemptive. That's a key difference. Now, I've heard some people kind of imply that Asyncio, this event-based stuff, just makes everything faster. Is that true?
That's a common misconception. The big performance wins for Asyncio are really in those I/O-bound scenarios we've been talking about.
Right. Managing the waiting time better.
Exactly. Reducing the overhead of switching between many waiting tasks. If your task is like heavy math calculations, constantly using the CPU-bound work, then traditional multi-threading or even multiprocessing might still be a better bet for actually using multiple CPU cores in parallel to get the calculation done faster. Asyncio's magic is about concurrency when waiting is the main activity, not raw computation speed.
Okay, that clarifies things. So Asyncio for waiting, maybe threads or multiprocessing for heavy lifting? Which means threads aren't like totally useless now, right? They must have some good points.
Oh, absolutely not useless. Threads definitely still have their advantages. A big one is often readability, initially anyway. With threads, you can often write your code more linearly. Like a simple sequence of steps. Do this, then that. The OS handles the complexity of running multiple sequences concurrently behind the scenes. It can feel simpler to write.
Like our thread bots just following their own recipe from start to finish, ignoring the others?
Pretty much, yeah. And another benefit is true parallelism with shared memory. Threads in the same program can all access and modify the same data directly in memory.
Which can be faster than passing data between separate processes.
Often, yes. Especially for large amounts of data. And let's face it, there's decades of knowledge, best practices, libraries, and existing code built around threading. It's a well-understood model, even with its complexities.
Okay, so threads have their merits. But then why is Asyncio gaining traction as an alternative, especially you mentioned for network programming?
Right, this brings us back squarely to the downsides of threads, particularly in network apps. We already hit the race condition problem hard. The cutlery example.
Yep, got that one. Shared data plus interruptions equals potential chaos.
Exactly, but there's more. When you start dealing with really high concurrency, like thousands of simultaneous connections or tasks, the overhead of the OS just managing all those threads, that context switching we talked about, can actually start to hurt your overall throughput. It becomes a bottleneck itself. Hattingh points out it can even be difficult to test with that many threads reliably on some systems, like macOS.
Wow. So the management itself becomes the problem.
It can, yeah. And that ties into the inflexibility issue. The OS scheduler gives CPU time to threads whether they're ready to use it or not.
Right, checking in on the waiting workers again.
Exactly. A thread waiting for network data might get woken up by the OS thousands of times, do nothing, and go back to sleep, wasting CPU cycles each time. Asyncio avoids that completely. A waiting coroutine explicitly yields, and it won't even be considered for execution until the event it's waiting for, like data arriving, actually happens.
Much smarter resource use.
Way smarter for I/O. You get more control. As Hattingh quotes from Apple's concurrency guide, writing correct, efficient, bug-free threading code is just hard because of system dynamics and coordination complexity.
Okay, message received. Threads. Powerful, familiar, but tricky, especially at scale with lots of waiting. So let's really get into Asyncio mechanics. What are the absolute must-know concepts?
Okay. At the very, very center of Asyncio is the event loop.
The event loop, the loop bot.
Exactly. Think of it as the conductor, the central coordinator. It runs the show. It keeps track of all the tasks, figures out which ones are ready to run, runs them for a bit, handles I/O events. It does everything.
Okay, the brain of the operation. And what are the things it manages? The tasks.
The basic units it manages are coroutines. These are the special functions you write with async def.
Async def, okay.
These functions have a superpower. They can pause themselves when they hit something that needs waiting, usually an await keyword.
Await, so async defines it, await pauses it.
Pretty much. When a coroutine awaits something, like await asyncio.sleep1 or await network request, it tells the event loop, okay, I need to wait here. Then it steps aside, handing control back to the loop.
So the loop can run something else.
Exactly. The loop finds another coroutine that is ready to run and starts or resumes that one. When the thing the first coroutine was waiting for is finally done, the loop will eventually wake it up and let it continue from where it paused right after the await.
That's the cooperative multitasking bit. They politely take turns via the event loop.
You got it. And these async and await keywords, introduced in Python 3.5, made Asyncio so much easier to use. Before that, it involved decorators and generators in a way that was less intuitive for many people.
Right, so async await is the modern way. Can we see like a super simple hello world-ish example?
Sure, it's pretty straightforward. You'd import Asyncio, maybe import time. Then you define a function with async def microroutine. Inside, maybe you print something, then await asyncio.sleep1 to pause for a second, then print something else.
Okay, simple async function. How do you run it?
You use asyncio.run. You just call asyncio.run, my coroutine. That function handles setting up the event loop, running your coroutine until it's completely finished, and then cleaning everything up nicely.
Asyncio.run. Got it. So that kicks things off. Now, what if I have multiple coroutines I want to run, sort of, at the same time?
Ah, good question. That's where tasks come in, an Asyncio task.
Tasks, okay.
A task is basically a coroutine that's been officially scheduled to run on the event loop. You typically create one using asyncio.createTask and pass your coroutine function call to it, like task, asyncio.createTask, my coroutine.
So create task puts it on the loop's to-do list.
Exactly. It schedules it to run soon. The loop will get to it when it can. Tasks are how you manage concurrently running operations.
And you mentioned something called gather.
Yes, asyncio.gather. This is super useful. If you have several coroutines or tasks you want to launch and then wait for all of them to finish, you use gather. Like results await asyncio.gather, coroutine 1, coroutine 2, task 3.
Ah, so it runs them all concurrently and waits for the whole batch.
Yep.
It returns the results once everything you pass to it is done. Great for parallel I/O, like fetching multiple web pages at once.
Very cool. Okay, what about futures? I see that term sometimes. How do they relate to tasks?
Futures, Asyncio future, are a slightly lower level concept. A future represents the eventual result of an asynchronous operation. It's like a placeholder, a promise that a value will appear later.
Okay.
Tasks are actually a specific type of future. A task is basically a future that knows how to wrap and run a coroutine. Honestly, for most day-to-day Asyncio use, you'll interact more directly with tasks via create task and gather. But it's good to know that tasks are futures underneath.
Got it. Tasks are the main thing we schedule and manage. Now, crucial question. What if I need to call some old regular blocking code from my nice new Asyncio program, like a library that wasn't written with async?
Yeah, that's super common. Lots of great libraries are synchronous, blocking.
Yeah.
If you just call a blocking function directly from your coroutine.
It freezes the whole event loop. The loop bot just stops. Exactly. Disaster. Everything grinds to a halt because that one blocking call ties up the entire loop until it's done.
Uh-oh. How do we avoid that?
Asyncio provides executors. You use the event loop's run-executor method. This takes your blocking function and runs it in a separate thread, or potentially a separate process, from a managed pool.
Ah, so it offloads the blocking work.
Precisely. It runs the slow blocking thing in the background managed by the executor.
Hmm.
Your main Asyncio event loop stays free to run other coroutines while the blocking call happens elsewhere. When the blocking call finishes, the executor lets the event loop know, and you get the result back via an awaitable.
That's clever. A bridge between the async world and the blocking world.
It's essential for mixing Asyncio with the existing Python ecosystem.
Okay. What about communication between different coroutines? If one part produces data and another needs to consume it.
For that, you've got Asyncio.q. If you've used threads, you might know Q.
Yeah, thread safe queues.
Asyncio. Q is the async equivalent. It's designed to be used with async await. One coroutine can await q.put item to add data, and another can await q.get to retrieve it. They handle the waiting and waking up automatically, so you don't block the loop while waiting for data to arrive or for space to become available in the queue.
Like an asynchronous conveyor belt. Nice.
Mm.
And resource management, like files or network connections, we use with in regular Python.
Yep, and Asyncio has the same concept. Async context managers use async with.
Async with, okay.
So if you have an object that needs setup and teardown, like acquiring and releasing a connection or opening and closing a file asynchronously, you can wrap it in an async with block. It guarantees the cleanup exit method happens even if errors occur. You can also create them using a decorator at async context manager.
Just like regular context managers, but async aware. Very useful for robust code. What about looping over data that arrives asynchronously?
That's where async iterators come in. You use async for.
Async for. Like for, but async.
Exactly. If you have something that yields items one by one, but getting the next item might require an asynchronous wait, like reading lines from a network stream, you use async for item in asyncerable. Under the hood, the object needs special ATR and async def annex methods.
ATR and annexed. Okay, sounds a bit complex to implement.
It can be, which is why there's a simpler way, async generators.
Like regular generators, but async.
You got it. You just write an async def function that uses yield. Inside that function, you can await other async operations between yields. It automatically gives you an async iterator without needing to write the ATR and annex class stuff yourself. Much cleaner for many use cases, like maybe yielding results from a database query one row at a time.
That sounds much more Pythonic.
Yeah.
So async def with yield. Cool. One last syntax thing. Async comprehensions.
Yeah. Just like listic set comprehensions, but asynchronous. You can use async for and even await inside the comprehension expression.
And also like a wait process item, async for item, and async generator.
Exactly. A concise way to build collections from async data sources.
Wow, okay. Event loop, coroutines, tasks, futures, executors, queues, context managers, iterators, generators, comprehensions. That's quite the toolkit.
It is. It gives you fine-grained control for building these IO-bound concurrent applications. And seeing them used in examples really helps cement the ideas. The book has some great case studies.
Yeah, like what?
Well, there's one building a simple message queue service. They start with a naive version using just Asyncio.streams, but then refactor it to use an Asyncio queue.
Using the async key we just talked about.
Exactly. It helps decouple the part that receives messages from the network from the part that distributes them to subscribers. Makes the whole thing much cleaner and more robust.
Makes sense. Good design principle. What else?
Another cool one involves 0MQAMQ. It's a library for high-performance asynchronous messaging like smart sockets.
Smart sockets.
Yeah, they handle things like reconnections and message patterns automatically. The case study shows how Asyncio makes it way easier to manage multiple AMQ sockets concurrently compared to traditional threading approaches with pollers. Much cleaner when using coroutines.
Okay.
They even build an application performance monitoring system using AMQ, Asyncio, AOTTP for a web interface, and server-send events to push real-time metrics to a browser. Asyncio manages the flow between the app sending data, the collector server, and the web visualization.
That sounds pretty complex, yeah.
Yeah.
Good showcase for Asyncio, managing different moving parts. And you mentioned AOTTP. That's the big one for web stuff, right?
Definitely the go-to for async HTTP in Python. The book uses it for both client-side making requests and server-side handling requests.
Okay.
There's a basic hello world server, but also a more involved scraping the news example. That one uses AOTTP as a server and as a client to talk to a service called Splash, which helps render JavaScript-heavy pages before scraping.
Oh, interesting. So it shows both sides.
Yeah, you see async with client session to manage connections and await session.det to make non-blocking requests. Really shows how you build apps that can handle lots of web traffic or make many requests efficiently.
Very practical. Any database examples?
Yep. There's a case study using Async PG, which is a fast async driver for PostgreSQL.
Async for Postgres.
Cool. It focuses on cache invalidation. Imagine you have multiple instances of your web app, each with its own in-memory cache to speed things up. How do you keep those caches consistent when data changes in the database?
Yeah, that's a classic hard problem.
They use PostgreSQL's built-in listen notify feature. Database triggers send notify events when data changes. Async lets the Python app await these notifications asynchronously. When a notification comes in, a callback updates the local cache.
Whoa, so the database tells the apps when to update their caches.
Pretty much. It's a really elegant solution using Async PG, database triggers, and an async web framework called Sanic. Keeps multiple caches synced without constant database polling.
That is clever. Using the database's own features asynchronously. Nice. The book mentions Twisted too. Isn't that another async framework?
It is, yeah. Twisted is another major and older async networking framework in Python. The book briefly mentions that Twisted can actually integrate with Asyncio's event loop, so you can potentially mix and match code from both ecosystems if needed.
Okay, interesting. So lots of powerful tools and examples.
Definitely. So, to kind of wrap this up, Asyncio really offers this powerful and often safer way to handle concurrency, specifically for those IO-bound tasks in Python.
Right. Safer than threads because of the cooperative nature, less risk of race conditions, and more efficient when waiting is the main game.
Exactly. It avoids the overhead and unpredictability that can come with preemptive multitasking in threads, especially when you have lots of tasks that spend most of their time waiting.
And even though it might seem complex when you first look at it, understanding those core bits, the event loop managing things, coroutines with async await, using tasks in gather, and handling blocking code with executors that really unlocks its power.
It does. It lets you build these really responsive, scalable applications that handle many connections or operations without getting bogged down. It's a different mindset, thinking about explicitly yielding control when waiting.
Yeah, actively managing the waiting instead of just letting it happen.
Precisely, leading to apps that feel faster and use resources better in the right scenarios.
So, okay, here's maybe a final thought then for you listening.
Mm.
Think about this whole principle, asynchronous operation. Managing waiting time efficiently by switching to other ready tasks.
Yeah.
Could that apply, not just in code, but maybe in your own life?
Yeah.
Your work.
Oh, interesting. Like when you're stuck waiting for that email reply.
Exactly. Or waiting for someone in a meeting. Instead of just sitting there, mentally blocked, could you switch to knocking out that quick 2-minute task that's also on your list? Improve your own productivity, maybe? Reduce that feeling of being stuck waiting.
Huh. That's actually a really neat parallel. Actively managing your own waiting periods by switching contexts cooperatively.
It's something to think about anyway. Maybe, try out Asyncio, dip into the docs, play with ATTP or Async PG, see what you can build with this different way of handling time.
There's definitely a lot to explore there.